In order to accomplish useful work with a pneumatic system, we need a device which can supply a sufficient amount of air at a desired pressure. The device which performs this function is called a compressor. Hi, I'm Dave Brown for Teletrain, and that's what we'll be covering today in Lesson 5 of Parker Hannafin's course, Industrial Pneumatic Technology. Compressors convert mechanical energy supplied by a prime mover, like an electric motor or a gasoline engine, into the potential energy of compressed air. There are two basic groups of air compressors: positive displacement and dynamic. The compressor shown here is a positive displacement type. It's called a positive displacement type because every stroke of the piston compresses a certain definite amount of air. As the amount of space in the chamber decreases, the pressure of the trapped air increases. Remember from Lesson 3, as volume decreases, pressure increases. This is a dynamic type air compressor. It operates on the principle of centrifugal force. We are adding kinetic energy to the air and forcing it to accelerate. This velocity energy is then converted to pressure energy for use in the pneumatic system. We'll be examining several different types of air compressors in this lesson, but they all operate on one of the two principles we just mentioned. Since you will want to identify a compressor in a pneumatic system diagram, you should be familiar with the symbol used to represent a compressor. Here it is. First, the most common type of positive displacement compressor found in industry today is the reciprocating piston compressor. The one you see here is a small two-stage compressor that's seen a lot of good use. Driven at rated speed, this unit will take 20 SCFM and raise it to a pressure of 100 psig. The motor is connected by belt to the crankshaft here. And here are the inlet and output ports. This cutaway of a single-stage compressor shows the major parts. Here is the cylinder body. The piston here is connected to this crankshaft, which is driven by a prime mover. These two valves here and here control inlet and outlet flow through the compressor. Let's see how it operates. When the crankshaft rotates, it pulls down on the piston, and the volume within the cylinder of the compressor increases, reducing the internal air pressure below atmospheric. This intake valve opens, and air at atmospheric pressure fills the chamber. At the bottom of the stroke, when the chamber is filled with air, the intake valve is closed. Now the piston begins its upward travel, reducing the cylinder volume and compressing the air. When the air pressure in the cylinder reaches a high level, the outlet valve is opened and the compressed air is discharged into an air receiver tank. The compressor we have just described is called a single-stage compressor. This is because it compresses air in a single stroke before it is discharged. Single-stage compressors are generally used in systems which require air pressures between 40 and 100 psig, although single-stage units capable of 250 psig are available. There are many different designs used in piston-type compressors, depending on the manufacturer. The pistons in these units may be either lubricated or non-lubricated. Here we see a piston from a compressor which must be lubricated. These rings, which form the seal between the piston and the cylinder wall, are steel, and during operation they are lubricated with oil. This piston is used on a compressor which requires no lubrication. Some of these pistons have piston rings like this, and this kind of seal, which is called a skirt. The rings, or skirts, are made from low-friction materials like graphite or Teflon. While non-lubricated compressors have a definite place in industry, you should know that they are less efficient and subject to higher maintenance cost than lubricated units. Right here we should mention one characteristic of single-stage piston-type compressors. Because air is being compressed with each revolution of the crankshaft, the output of a reciprocating type unit may have severe pulsations, especially if it is closely coupled to the load. To minimize this, most systems use a receiver tank to absorb the pulsations and help smooth out the airflow. As we will see in later programs, receiver tanks serve other functions as well. The vane compressor you see here is a positive displacement compressor. It's a rotary type, and it can develop a relatively smooth flow of pressurized air. This is the drive shaft, and here are the inlet and outlet ports. Inside the housing is a rotor, which supports these floating vanes. The rotor is connected to a prime mover by means of this shaft. As the rotor turns, the vanes here are thrown out by centrifugal force, contact the housing, and form an airtight seal. The shaft is off-center so that the volume between the vanes changes as the rotor turns. You can see that the volume in the area of the inlet port increases as the shaft turns. This reduces pressure here, and atmospheric pressure fills the chamber with air at atmospheric pressure. Here on the outlet side, the volume between vanes is decreasing, causing the pressure of the air trapped between the vanes to increase. The compressed air is discharged through the outlet port into an air receiver tank. Since they must slide easily against the housing, vanes are typically made from carbon or other low-friction materials, like these made from cloth that's been impregnated with phenolic resin. For small displacement applications, the vane-type compressor is a relatively economical unit. It has a low operating cost and requires a low starting torque. Vane units are available for pressures up to 150 psig and with power ranges from fractional horsepower all the way up to 500 horsepower. Let's take a look at another rotary type compressor. This is a helical compressor. It's called a helical compressor because it develops compressed air by running two meshing rotors called helixes against one another like two screws. In fact, you'll often hear it referred to as a screw-type compressor. Here is the drive shaft, and the inlet and outlet ports here and here. As you can see, these two helical screws mesh and rotate together. As air comes in, it gets trapped between the screws. Since the volume between the helixes decreases as they turn, the air is compressed and exits at a higher pressure. There are two basic types of helical compressors, the dry and the oil-flooded. The maximum pressure you can get from a single-stage dry compressor is about 40 psig. Timing gears are used to turn the screws and help maintain a constant clearance. Since the screws don't touch, dry compressors are not lubricated. Dry helical compressors have a good efficiency if they are run at high speeds, and they are used primarily for applications where oil-free air is required. Oil-flooded compressors, like the one we've already looked at, are available in a range from 7 to 1,000 horsepower. Because the oil gives you a better seal between the helixes and acts as a coolant, The oil-flooded compressor can be operated at lower speeds and higher pressures in single stage than the dry type. There is one characteristic to keep in mind, though. An oil separator is required to remove the oil from the air. The lobed rotor compressor is still another type of positive displacement compressor. It can develop pressures up to 250 psig and is available at ratings from 7 to 3,000 horsepower. This illustration shows how the unit gets its name. Inside the compressor housing are these two rotors, which mesh as they turn. A timing mechanism is used to control the movement of the rotors and to prevent clearance problems between the rotors and the pump housing. Air coming in at the inlet gets trapped between the rotors and the housing. As the air is displaced toward the outlet, the volume decreases, causing the air pressure to rise. In actual operation, the rotors do not touch, so a certain amount of slip exists. That is, some air can leak back between the rotors while it is being compressed, and the amount of air that will leak back increases the higher the output pressure becomes. Lobed rotor compressors should always be operated at maximum speed in order to obtain the highest efficiency. The compressor you see here is a dynamic type. It is a centrifugal compressor, and it's best suited for applications in which a large volume of air must be moved, but at relatively low pressure. Although in multiple stage designs, they can achieve pressures comparable to the other types. This compressor housing encloses a moving part here called an impeller that is driven at high speed by a prime mover. When the impeller turns, these blades here draw air at atmospheric pressure into this inlet port. Since they are turning at high speed, the blades accelerate the air as it is moved within the compressor body. A diffuser and collector are located in this area. They convert the velocity energy acquired by the air to pressure energy. Here is an important point to remember. With a centrifugal compressor, air demand in the system should never be allowed to drop much below its rated flow. If this is allowed to happen, the compressor will become unloaded and surging will occur. What this means is that the pressure field at the output will become unstable, and if it is allowed to continue, bearings, blades, and even the housing may be damaged. The basic principles which make a centrifugal compressor work are used in two compressor designs, radial and axial. These terms simply refer to the way in which air is directed through the compressor. For example, this is a multi-stage radial compressor. As you can see, as air is moved through the compressor from the inlet here to the discharge here, it follows a path through these impellers that is radial to the shaft. It's called a multi-stage compressor because there are several compressors being operated in series to obtain a higher output pressure. Radial compressors operate at extremely high speeds. In the aircraft and aerospace industries, they often run between 50 to 100,000 RPM. In commercial applications, typical speeds are about 20,000 RPM. Here is a drawing of a typical multi-stage axial compressor. Here, the impellers or blades are mounted both on the rotor and the inside of the compressor housing. As the rotor is turned, air enters the inlet here and is forced through the compressor to the output port here. Axial compressors generally have a smaller diameter than the radial units, and for that reason must run at a slightly higher speed to develop the same output. Axial compressors are best suited for applications where high volumes of air must be moved, for example, in a blast furnace operation. For high pressures, it is more efficient to compress a gas in several stages rather than try to do it all at one time. One fairly common unit that will do this job for us is the two-stage piston compressor you see here. Basically, it consists of two piston-type compressors, one large and one small, connected to the same crankshaft. This larger cylinder performs the first stage of compression, and the smaller piston compresses air in the second stage. This unit is called the intercooler, and we'll explain its function in a minute. The pistons for both the first and second stages are connected to the same crankshaft, here. And both compressors, or stages, have their own inlet and outlet valves here and here. The intercooler connects the outlet of the first stage to the input of the second stage. Its purpose is to cool the air as it flows from the first to second stage. Let's assume a prime mover is turning the crankshaft and moving the large piston in a downward stroke. Air enters the bore through the open inlet valve here. When the piston begins its upward stroke, the inlet valve is closed and pressure builds within the chamber until it reaches a high pressure. Then this outlet valve is opened, which allows the hot compressed air to discharge into the intercooler. During the travel time through the intercooler, the compressed air is cooled either by air or water that passes over the intercooler. So when it reaches the second stage, much of the heat from the first compression has been dissipated. And since the air is now cooler, more of it can fit into a given space. Therefore, the cylinder in the second stage can be smaller than the first stage. The stages are interconnected so that when the piston in the first stage is moving upward, the piston in the second stage is moving downward, and its inlet valve is open. The compressed air from the first stage enters the chamber. When the second stage piston begins the upward stroke, the inlet valve is closed. Pressure builds, and when it reaches a high enough value, the outlet valve is open, allowing the compressed air to discharge into an air receiver. This completes the second stage of compression. You can see from the diagram that in normal operation, one stage is pulling in atmospheric air to be compressed, while the other stage is receiving compressed air and discharging it at a higher pressure. If you're thinking, hey, the air from the second stage is hot too, you're right. But because of the intercooler, the temperature at the output of the second stage is not as high as it would be if we tried to compress the air to the same pressure in just one stage. The end result is two-stage compressors are more efficient and do not require as much energy as single-stage units delivering the same pressure. There are several methods for unloading a compressor in use today. Here are some we'll examine. Bypass, start-stop, inlet valve regulation, inlet throttling, and inlet closure. The first method is called bypass. With this technique, we bleed the compressed air to the atmosphere at high pressure. Unfortunately, this type of control causes the compressor to run under full load at all times, which is hard on the compressor and wastes energy. Remember this device? It's a pressure switch, which we described back in Chapter 4. It's used to start and stop the motor and is primarily used on small units. This is because frequent starting and stopping of an electric motor can cause excessive heat buildup, particularly in larger units. Another method is called inlet valve regulation. And with this method, a mechanism is used to hold the inlet valve open when there is no demand for air. What this does is to allow the air to pass freely in and out of the cylinder as the piston moves up and down in the bore. So although the compressor continues to run, it's not compressing air. This is the most widely used system on larger compressors. Somewhat similar to this is a technique called inlet throttling. Inlet throttling increases or decreases the restriction at the inlet port of the compressor so it regulates the amount of air admitted to the cylinder. In effect, it's like decreasing the capacity or size of the compressor. A disadvantage with this method is that it wastes energy. The final method of unloading is to close the inlet valve. The compressor is actually working in a vacuum. The only power the prime mover delivers is to overcome the mechanical friction. Although total closure does allow us to unload a compressor, it is an inefficient technique, and for that reason is seldom used today. Well, we've seen that all of these controls for unloading a compressor affect its performance and efficiency. Can you think of any other factor that would reduce the amount of air at the inlet? How about altitude? Remember back in Lesson 2 where we explained the relationship between altitude above sea level and atmospheric pressure? This chart shows how the pressure of air available at the input of the compressor decreases the higher you are above sea level. That is, the higher you go, the lower the air pressure or density. This is an important relationship to remember because it changes not only the power needed to drive the compressor, but the compression ratio and compressor capacity as well. In fact, one of the major factors an engineer will take into account when designing a system is the reduction in compressor capacity due to altitude. This chart for single-stage compressors shows capacity correction factors for different operating pressures. For example, if you were in Denver, which is about 1 mile above sea level, and had a system operating at around 90 psig, the capacity of the compressor in your system would be reduced to 0.917 of its rated value, almost a 10% decrease. That means you'd want to select a compressor with a capacity larger than if the same system were going to operate at sea level. The main point to remember is that as altitude increases, the output capacity of an air compressor decreases. It is more critical with single-stage compressors, but is also a factor with multi-stage units. Compressed air system sounds can come from many sources, the main one being the compressor itself. And because prolonged exposure to certain levels of noise and sounds may result in impaired hearing, there is increasing concern for the noise a compressor generates. It is so important, in fact, that the Occupational Safety and Health Act, or OSHA as it is called, has developed guidelines and specified protection devices. You should always follow your plant's safety rules regarding different types of ear protection. In the process of compressing air, approximately 50% of the input power ends up as heat. This heat must be disposed of in some way. Part goes into the cooling water if water is used, but the rest goes into the surrounding air. Therefore, exhaust fans are usually an essential part of the system, particularly if the compressors are in an enclosed area. We should mention briefly that there are two main factors to be considered when selecting a compressor for a pneumatic system: the compressor's size and the number of compressors. Size selection is important and to a large extent depends on how much compressed air is required and how much more may be needed in the near future. You'll probably want to have standby capacity for emergency situations. and often this can be accomplished with the addition of external piping so a mobile unit can be connected. One reason for considering more than a single compressor is that with 2 or more compressors supplying a system, you'll have some backup capability in case one fails or is shut down for maintenance. Here are some other tips when you're planning a new system or making changes to an existing one. First, try to get the compressors as close as possible to the point of use. Savings will be in shorter supply lines and lower pressure drops. Remember, your compressor likes cool, clean, dry air, so keep air intakes away from dusty yards, parking lots, or smokestacks that might contain contaminants which can damage the compressor. Have you ever been up on the plant roof on a summer day? If you have, you know how hot it can be, particularly if the roof is black. This is not the place to locate an air intake. As air temperature increases, its volume increases, and the compressor has to work a good deal longer to deliver the same capacity. So locate intakes where the air will remain as cool as possible. Intake air should be filtered. Filters are made by a number of manufacturers, but they are all intended for the same purpose: to remove particles from the intake air that could damage the compressor. Filters may be one of 3 types. 1, dry filters use a felted cloth or paper as the filter medium. 2, viscous impingement filters have woven wire in cells or frames which are coated with oil. And 3, oil bath filters, in which the air is cleaned by a scrubbing action in oil and dirt is washed down into a sump. One last point: when filters get dirty, they present a high resistance to the flow of air to the compressor. Filters should be serviced at regular intervals, so make sure you follow the schedule required at your facility. This concludes Lesson 5. Don't forget to complete the exercises you'll find on page 48 of your text. I'm Dave Brown for Teletrain.